have DING and MOFC. So DING is here and MOFC there. Okay, so after the unrest started, we installed 3 new continuous stations in the area. So 2 within the main Askja caldera. This is Yonk and Kask that you can see on the map. And then Tank, which is on the most northern rim of the caldera and essentially transmits the data. Okay, so historic eruptive activity at Askja volcano comprises both large, essentially explosive rhyolitic eruptions, and also basaltic effusive eruptions. So the last eruption to occur here was in 1961. And essentially this was a small basaltic fissure eruption. So the fissure actually opened up here. It was 800 meters long. And this produced a lava field with a volume of about 0.1 cubic kilometers. So just to give you a reference, this is a bit smaller, essentially, than the volume that was extruded during the first Fagradalsfjord eruption in 2021. So the most recent caldera, or explosive eruption to occur in Askja was in 1875, and this was actually part of a major rifting event between 1874 to 76. So the caldera that actually formed is Lake Ørskjevær, so that's the one in the center here. And it also formed a small explosive crater called Lake Beatty, and that was actually shown on the first slide. All right, so prior to the onset of this inflation, long-term subsidence was occurring at Askja. If we have to take a quick look at the next slide, this is the long-term leveling data acquired by Eric Sterkel. And this slide is essentially showing the data since 1968 to before the inflation started in the summer of 2021. So we can see here this initial subsidence was actually occurring from 1968 to 1970. Following that, we have this quite sharp change to inflation. We then have a gap in the measurements, unfortunately, and this is because of the Krapler fires during this time. And then when the measurements resumed again in 1983, you can see that we have continued subsidence occurring at the volcano, but at a far reduced rate. So the suggested processes behind this long-term subsidence have essentially included cooling and contraction of an existing magma body, plus magma outflow potentially, and also viscoelastic effects. So the GNSS observations at OLAC suggest that this change to inflation actually occurred at the end of July 2021. And the inflation, of course, is also observed on INSAR. You saw this from Adriano's presentation earlier, and also on the leveling profiles that have continued. Okay, so here we're just looking at the previous subsidence that was occurring. So as I said, the leveling measurements show this from 1983 onwards. Here we're just looking at sentinel interferograms on the top panel from 3 different tracks. So here we have 2 descending and 1 ascending. So here we see the subsidence signal in blue amplitudes here. And on the bottom panel, we've got the near east, essentially the decomposition results, the near east and the near upper vertical displacements. So they show that essentially the maximum center of the deflation was situated to the north of the Ørskjevær caldera. Okay, so here again, now we're just looking at a series of interferograms, but this is from the inflation period onwards, so from July 2021. So on the left-hand side here, we've got both the wrapped and unwrapped interferograms. Now these are spanning from end of July 21 to September 2021. On the middle section here, we've got one of our campaign GPS time series, and this is from the mid-Askja station, and essentially this is situated in the main Askja caldera. And on the right-hand side, we've got the time series from OLAC, which is the continuous GPS station. Okay, so here we clearly see the subsidence that was continuing, and then a sharp change to uplift on the campaign site, and the same for OLAC. Okay, the subsidence here, and you can see the magnitude of the inflation compared to the subsidence that was occurring previously. All right, so if we look at the time series from both the GPS data and the INSAR, it seems that actually the source of this inflation was not static during an extended time period. So what we see looking at the INSAR, so here we've got essentially the decomposition results from from July to September 21 on the top, and on the bottom from September 21 to September 22. And you can see that there's a shift in the main location of the inflation signal that's observed. So essentially, originally, the signal was centered around our GPS station, OLAC, and after that time, the signal rotated actually in a clockwise direction further to the north. If we look at the GPS time series now, we can see at the start or the onset of the inflation, the initial rate was significantly higher. After September 21, the rate is actually reduced, and then since this time, the rate has been stable and the source location has been stable for this inflation. So what I would suggest is actually the data could be modeled using two separate sources in these two different time periods. So also if we have a look at the decomposition results shown here, so on the left-hand panel, we've got again July to September 21, and on the right or the middle panel, September 21 to September 22. And now if we look at some transects through these decomposition results, we can see that in time period 1, here we look at the near-up displacements, and this is, in the blue-purple colors for the first time period, T1. Here we can see the nice inflation signal over the caldera. This is the west-east transect going through here. But we can see actually on the eastern side, it's showing subsidence. We don't see the same signal in the latter period. So what we've actually done, as I said, modeled this as two separate time periods and using different sources. So in T1, we actually have two sources required to model the deformation that's observed. So we have an inflating sill-type source, which is shown by essentially the black polygon shown here. And then we also require a deflating source to match the subsidence signal that was observed on the decomposition result. And that's shown here by this magenta sill-type source. So both are near horizontal sill-type sources. However, the upper one, located at a depth of just below 3 kilometers, is inflating, and a lower one, located at a depth of about 4 kilometers, is deflating. Okay, for the second time period, this can be modeled very well just using a single source. So for time period 2, where, as I said, the signal is broader here, and the source seems to have migrated to the north. This can be modeled using a single Arcata dislocation, again at a depth of about 3 kilometers. And the volume change associated with this is about 11 million cubic meters. So if we take a look at the seismicity as well, since the onset of the unrest, this is also quite interesting. We don't see a significant increase in seismicity that we see associated with unrest periods at our other volcanoes in Iceland. For example, associated with dike intrusions, but also sill intrusions. So here we're looking at seismicity for earthquakes greater than magnitude 0.5, as this is the magnitude of completeness here. And on the left-hand side, you can see the map, and with the blue box is essentially the region that I've extracted the earthquake information from. So if we look at the panel, okay, so this is earthquake activity since 2016, and I've chosen that date because this is after the Bardabunga eruption. Okay, so here we see a slight increase in the start of the unrest, but essentially after that time, it just reverts to background levels. However, if we break up the seismicity and look at different areas, then we do see more subtle changes. So here we're just looking at the seismicity, again for the same time period since 2016, but for the area which includes Eskivart, which is the lake here, and the western side of the main Askja caldera. And in this case, again, we see an increase in the seismicity at the start of the unrest, end of July 21. It then flattens off briefly, but then starts to increase again. If we look at seismicity just in the known geothermal area, now this seismicity here has been occurring for decades, so it's not something new. If we actually look at this, it's very difficult to see any change whatsoever in the slope related to this unrest. Okay, so what is the cause of this inflation? Well, for T1, I mean, the modeling is suggesting that this is upward migration of magma, essentially just within the upper part of the volcanic plumbing system beneath Askja. So here we have a movement from about, let's say, 4 to 3 kilometers depth. So a deflating source at about 4 kilometers with magma rising to a slightly shallower level. However, for the second phase of inflation, we don't see any evidence for this shallow subsidence source. So here, this may be triggered by an influx of new melt from much deeper within the plumbing system, so possibly greater than, let's say, 16 kilometers depth. The total estimated inflation volume for the unrest to date, so using these shallow sources, is about 25 million cubic meters. So I do want to say, of course, this is just one of many models to come. You saw an alternate model presented earlier today by Adriano, essentially with an inflating sill and movement on the ring fault system. What I've shown you here is essentially a series of models. Well, two sources, or so I should say two sources in T1 and a single source in T2. And this, of course, assumes a uniform elastic half space. So initial finite element, more complex models have already been run by one of the students based at University of Iceland, and her model incorporates topography and heterogeneities. And this actually suggests that the depth of the inflating source could be up to a kilometer deeper than I've shown you here. So I just want to say I think it's very important to run these different types of models. I've shown you a simple analytical model which I believe can reproduce the deformation observed, and it also corresponds with other data sets. So the gravity, the seismicity, the geochemistry, etc. But it's very important to run more models at Askja, and many more will be run in the future with added complexities. And these models hopefully give us a better understanding of the subsurface plumbing system and also the uncertainties involved in the individual models. Okay, thank you. I forgot the last slide, but if you have questions about future scenarios, then please just ask. Yes?
Oh, you need to wait for the microphone.
You mentioned gravity. Are there some gravity data available?
There are, and in fact, a paper has just recently been published by Matthias. Is Andy here? No. Yep. Andy, what was the journal this was published in? No, sorry, neither can I. So yes. So the initial gravity results essentially indicated no mass increase beneath Askja. So this was for the initial period of the unrest. I mean, of course, there are some uncertainties, in the data and this study. But I mean, in reference to this would support the model that we present here, for essentially initially in phase 1 or T1 of existing magma just migrating up to a shallower level within the system. I guess we'll see what the next gravity results show from this summer.
Catalina was right. Well, why don't you give it to Catalina? She's right behind you.
Hi, I have a question about the model because, well, this model with the two narrow sill, it sounds a bit like a weird animals, right, in terms of magmatic source. And, well, I saw it's mainly based on the fact that in the vertical, you see this signal that needed to be explained. So my question is that could it be the fact that because the deformation was much sharper at the beginning, that assuming that there is no north component gets mapped in the vertical, and maybe a solution could be if you have the GPS, you could just remove from the north component projected
Yeah.
And then solve this, because it seemed like the information is a lot. So even the noise component, sometimes, it's a small percentage, but of a big number.
Yeah.
And because I noticed that the first time period is,
If you,
if you thought.
yeah, no, so yes, certainly it could be related to noise in the input interferogram. So for this model, actually for both time periods, we include 4 sentinel interferograms, 2 ascending, 2 descending. Also data from the continuous stations, but of course in T1, this is less data because we don't have the data from the 3 additional installations that were done after the onset of the arrest. Plus, it includes data from 4 campaign GPS stations. But, so yes, part of it may be related to noise, but also if you look at the probability distribution functions for that inversion, the width of the sills is not well constrained. So for the second period, it's really quite well constrained. And the depth is for both, but the width for T1, so yes, there's quite a big range, right? So they could be significantly wider than from the optimal model that I was showing you on the screen.
Thanks.
Paul, do you still wait for the mic?
Is the lake doing anything? Changes in lake level or getting hot or cold or?
Yeah, so we just did a campaign in August, end of August, and essentially we went to VT. Let me bring it back up. Okay, so this is VT Lake in the foreground here, and in the background is the Erskivat caldera. So this caldera formed after the explosive eruption in 1875. This is an explosive crater, which also formed during our eruption. So we routinely do gas measurements on both, so at VT and also on the southwestern edge of Erskivat. So to answer your question, so far there has been no change in concentrations of the gas measurements, no change in the ratios of the gases, no change in the temperature of the fumaroles that have been measured. However, there has been a slight increase in the temperature of the water in both VT and in Erskivat. However, I say that it's very clear from this year that the lake level is significantly lower on both. So in Erskivat, it may be due to the inflation. So in fact, more fumaroles are now exposed that were under the water previously. And in BT, we think essentially this is just due to the fact that last winter was nowhere near as harsh as the previous one, so there was much less snowfall, and I think there's less groundwater infiltrating the lakes, infiltrating BT. So this alone could explain a slight increase in the water temperatures that we're observing. It is not really significant. We're talking a few degrees increase.
There's no CO2 bubbling out.
Well, yes, we measure CO2 in the fumaroles and H2S, but we haven't seen any change in the concentrations or, the ratios of the gases.
Yeah, that was a really interesting talk, Michelle, and I'm wondering if this low seismicity or this really non-remarkable seismicity that you show is normal for the volcanoes in your part of the world, or what did you expect, in other words?
No, usually I would say no, and we expect to see a significant increase in seismicity when we have a new intrusion. Yeah. So the question is now, is the lack of seismicity because the volcano was subsiding first for nearly 50 years, So, of course, the stress in the upper crust has been perturbed as a result of this, and maybe it's just going to take much longer for the stresses to build up to that level where we start triggering, the seismicity, the fracturing that would be expected. To be honest, I don't really have an answer for it, but it's intriguing.
Okay, we should move to the next talk, which is Volk Ameling, and he'll be talking on what's next for Mauna Loa volcano, stress changes due to the 2022 intrusion and eruption.
Yeah. Okay. Okay, so I'm going to talk about, as Paul just said, about Mauna Loa. It had a big eruption last year, finally. The topics I'm going to talk about are, giving an overview, about 20 years of deformation data. Then we did a successful prediction of the location of the eruption. And I'm going to talk about a very interesting earthquake at the summit prior to the eruption. Okay, we have, Mauna Loa, the big island of Hawaii. The two volcanoes are Kilauea and Mauna Loa. They are characterized by rift zones. Mauna Loa has a rift zone which goes through the Okay. It has a rift zone which goes through the entire volcano. Eruptions typically they start at the summit and then they go in. A dike propagates into one of the rift zones, and previous eruptions at Mauna Loa happened in 1950, 75, and 84. So it was 38 years since the last eruption. But in some time periods, it's extremely active. In the end of the 19th century, it had an eruption every couple of years. For the structure of the volcano, something which is important is the big décollement at the base of the volcano. Mauna Loa, by the way, is the largest volcano, largest mountain on Earth, about 9 kilometers from the ocean bottom to the top. And because of the growth, magma intruding into the rift zone, there's occasionally earthquakes on the décollement fault at the base of the volcano. What really matters is whether an eruption occurs from the northeast or from the southwest rift zone. If it happens from the northeast, the slopes are not very steep, but in the southwest, they are extremely steep, and so the flows can be very fast. Here's a giant flow from the 1950 eruption. And in this eruption, it took only 3 hours from the moment the eruption started until the coast was reached. And since then, there has been lots of coastal development, beautiful hotels like this one. And there's, of course, concern whether for eruption from that, whether there will be enough time to evacuate people. Just a beautiful picture of the eruption from 22. Luckily, it went to the northwest rift zone, so it didn't pose any danger, any hazards to people living there. It was just a beautiful eruption going on for 2 weeks or something like that. And so something what also happens at Mauna Loa, I mentioned the décollement the pretty frequent décollement earthquakes. Generally, when you have rift zone eruptions in the 1 or 2 years before an eruption or after an eruption, there is a décollement earthquake. So what is happening is you're putting the volcano, the flanks are moving apart, and that creates space for magma to intrude into the rift zone. And once magma has intruded, then it pushes on the décollement fault, and that's what leads to the décollement earthquakes. Since 2002, we have continuous GPS measurements. There was a period of intrusion back in 2004, 2010, and then on the left side, on the west flank, you see that nothing happened for a couple of years, and in 2014, it started to inflate again, and that then continued until the eruption happened. And you see a significant difference between the west flank and the east flank. Actually, there's a factor of 2 different in the y-axis, and in the east flank on the right, it never stopped flank deformation. On the western flank, it did stop. So during this, we have excellent INSA data of this intrusion period, largely starting with the Cosmos SkyMed INSA data from the Hawaii supersite. The INSA essentially all the time shows almost the same signal, and there's secular seismicity happening once in a while, some swarms. The INSA data or the geodetic data can be best explained with a little weird magma model. So it's a dike-like magma body, just sort of lined with the rift zone, rather in the south of the caldera. But it's not the dike-like magma body is not the only thing. Then you also need the inflation source to the east of the rift zone. So it's a dual body magma reservoir, and that explains in particular the asymmetry in the vertical deformation. It shows vertical deformation. So inflation during these different time periods was almost the same, but in 2015, 2018, for this time period, you can see that the inflation pattern shifted to the south. Somehow this magma body moved, and after that it moved back further back to the north. What could be essentially it's exactly the same pattern since 2018. What was observed during 2014-15 and in the previous inflation period. So what could be the explanation for that? One possibility. So that there is explanation for the magma body to move southward. One explanation could be stress changes from the Coleman slip, but they are associated with a symmetric stress change. So there's not really a reason for the magma body to move southward. The stress change due to the magma source, it's again symmetrically uniform around the dike. But the topographic stress field is different. The topographic stress field topography decreases to the south. That creates a topographic stress gradient stronger in the south than in the north, and we think that is the reason why the magma body migrated southward. And so it's a summary of what happened up to 2020. During 2000. The magma body moved to the south, and if you look at the stress field after this, the stress field is most extensionally north of the magma body, and then of course the magma, the dike could also propagate upwards. So then we had the 2022 eruption, and sure enough, the eruption happened from the northeast rift zone, which of course was good because no hazards, and so the stress changes, with the stress changes, we have essentially predicted the location, not quite the precise location, but the general location of the dike, which sort of shows that the stress change models work well. But I have to admit, the random chance was pretty good because there's only two possibilities where the magma could have gone. Okay, now we'll talk about the 2002 eruption. The volcano continued to inflate, and then a couple of months, 2 months prior to the eruption, inflation became pretty rapid, a factor of 2 faster than before. This shows the that was before the eruption. And after the eruption, it shows the horizontal displacement. So there was rapid deformation immediately after the eruption. I'm not going to talk about the eruption itself very much because there was so much deformation. It's difficult to interpret what has to be done, of course. But so after the eruption, there was this a significant decay of the reinflation rate, as we have observed at other volcanoes, of course, as well. So what do the GPS vectors show. So this is a period prior to the acceleration of deformation. It shows the typical pattern. If you go a little bit for the last 2 months prior to the eruption, there's a difference. There's the vectors are much larger close to the caldera, which indicates there was somehow a very shallow source active or more magma going into shallow levels than previously. During the eruption, okay, that's a deformation due to the dike. There was about more than a meter of deformation, and then later on during the eruption, we see deflation from the reservoir evacuation, and after the eruption ended, it ended on December 12th. We see reinflation in the north and still continuing deflation in the south. So that indicates some magma migration within the reservoir. In the early pre-eruptive period, the vectors are, well, rapid reinflation, long vectors, very close to the caldera. So again, magma going up, inflating at very shallow levels, and a little bit later, there is relatively less inflation directly at the summit. So indicating magma intrusion at deeper levels. Yeah, and okay, so just again, this typical inflating pattern over all the time period, that is what it shows here. And now it is getting closer to that what we had previously. Still a little bit more inflation close to the summit, but it's decaying. So the shadow source is is more active at the moment. And that, of course, is also seen in the insert. This is a vertical. I haven't done very much of that yet. The vertical and the horizontal clearly shows that in the post-eruptive period, deformation is much more concentrated, again, indicating the shallow reinflation source. Okay, if we look at the longer-term picture, this shows the horizontal GPS on both flanks again. It was a big eruption, but in the overall picture of the volcano, it's just a blip, not very significant. Something which is striking, as I said before, is that in the eastern flank, there was deformation all the time on the flanks. On the western flank, not. So what could be the reason for that? And Mauna Loa is, it's very big, 4 kilometers high, more than 4 kilometers. So you get significant orographic rainfall. And there's easterly trade winds all the time. So we would expect more precipitation, or there's more precipitation on the eastern flank than in the lower flank. So one possibility could be would be nice to figure out that the precipitation, infiltrated rainwater, plays a role for the continuous eastern flank deformation. Prior to the eruption in March 2021, there was a magnitude 3.6 earthquake at the summit. You can nicely see the fringes. It ruptured. The surface. It ruptured the caldera floor. Something what we sort of would expect. You inflate the volcano, and then you start to get earthquakes. There was the insert time series shows that there was in the 2 months prior to this earthquake, there was significant increase in inflation, so it turns out so this earthquake was on March 6th. Couple of days, a day later, 2 days later, there was floods on Hawaii. Actually, unfortunately, not on the island. Well, fortunately, okay, I don't want to get into that. For my science, unfortunately, not on the big island. It was on the island of Maui. 160 kilometers from the distance from Mauna Loa. But okay, there was something similar precipitation at Mauna Loa. It could have maybe contributed to this shallow earthquakes, to this shallow earthquake. And we had a paper published a couple of years ago. The 2018 eruption of Kilauea, it was preceded by very significant, the most significant precipitation over quite a long time. So we are saying that yeah, maybe the water contributed to it, though it's controversial, but there's not much, you can't really say much about the rainfall data. It was just much more wet. And so it turns out so this is now a time series of precipitation derived from the Global Precipitation Measurement Mission for Mauna Loa. There was significant precipitation as well. It just shows the last or total period of 14 months, but in the last 2 months prior to the eruption, about 40% of the precipitation happened. So it was a factor of 4 or 5 more precipitation than normal. So it could have well contributed to this earthquake. It was very shallow. The rainwater infiltrates and maybe it helped to move forward. Okay, that's all what I have. Thank you for your attention.
Okay, we have time for a quick question.
Thank you for the presentation. So maybe I didn't quite follow. So you said that maybe there is a triggering of the 2018 eruption due to precipitation, but you also used the precipitation factor to perhaps explain the asymmetry of flank motion across the rift. Is it right? Could you elaborate, please?
Yes. So the 2018 eruption that was a Kilauea. It was a different volcano. Yes. And so what I think, so the eastern flank of Mauna Loa, it's moving all the time, slowly, and that is a flank which receives more precipitation. So maybe the precipitation is the reason for that. And then we had this earthquake in 2021, which happened after significant precipitation. So precipitation could matter quite a lot to modulate this volcano. Of course, it's difficult to prove. But basaltic rock, it's very easy well, it has lots of cracks, so water can go pretty deep and then accumulate. And if it accumulates at a fault or something, then you have higher water pressure, pore pressure. And we know that pore pressure is what can trigger earthquakes also.
So in other way, in order to explain the asymmetry with precipitation, you need to have a fault, lubrications somehow. So you need to incorporate a fault in your model. Yeah.
Yes. Okay. So I didn't talk about it. We used to have the fault in the geodetic models at the base of the décollement, but there's actually no constraints from the geodetic data. You can put it anywhere, and the data just don't have this resolution. So there is to explain the geodetic data, you need a fault somewhere, and we have it. Yeah.
Okay, thank you very much, Volk. The next speaker is Patty Mothers, talking about variable ground deformation at Chile's volcano on the Ecuador-Colombia border.
Thanks. I'm going to move this closer.
You're okay.
Okay, so how do things work? But which is,
Pointer
how
to
do you
work.
point it?
The pointer's not working.
Oh, it's not working.
Well, it worked for Michelle, but
Oh, okay.
pointer.
Try this one.
Yeah. There you go.
It was.
Okay, good afternoon, everybody. It's a pleasure to be here. And this is my first Fringe meeting, by the way, so it's great after a long time of not going to meetings. So the work I'm doing is a work in progress, and it deals with the variable ground deformation rates that we've observed. Actually, we've observed them since 2014, but especially now in May 2022 at a volcano on the Ecuadorian-Colombian border. And I'd like to give credit to my co-authors, some of the Instituto Geofísico, Pedro Espín, who's here doing his doctorate, and Mauricio Battaglia, and also colleagues from the Colombian Geological Survey, and also give credit to supersites because Ecuador is a supersite. So what is the motivation that I want to talk to you about? So we have really strong ground deformation. It's been seen up to, not on the average of recently, especially since 2022, of about 9 centimeters a year at these two, especially one volcano without an eruption in about 15,000 years. And what patterns do we see between the ground deformation and the seismicity? There's 2 activity nests. And by combining, eventually combining, because as I said, this is a work in progress, the INSAR and GPS time series, I'd like to be able to derive and improve propagation models and also where do we think we're going. What other volcanoes are analogs for this case? The one I come up with is Campi Felibre, possibly, and producing at times this situation of over 5,000 earthquakes a day. And that is 600,000 earthquakes since 2014. So will this volcanic system erupt? That's the big question. And when you're sitting there watching all the earthquakes come in at my observatory, you know, now we have a little bit better understanding of it. But if Susie was there back in 2014, and I think Juliet also, it's a very disturbing thing. And we're not talking about little quakes necessarily, but a lot of them are felt earthquakes. So the areas up along the Colombian Ecuadorian border, we have the Pacific Ocean here, and this little square encompasses a zone. And it's cut by faults, some which are related to the movement of the North Andean sliver, moving up to the northeast because of the collision of the Carnegie Ridge and the Nazca Plate. But anyway, this is the volcanic area here, and we've had 2 earthquakes since 2014 that are 5.6 magnitude. This one here with the star, and this one here last year in July. And then there's another one that was felt here in a community of 4.3, and another one here in 1868, a 6.7. A study was done with receiver functions and using our seismic network, which is not, especially when they use the data, was not very dense at that time. And it shows slow velocity zones, and this is starting in the north and going southward. And it shows that there's a possibly slow velocity zone suggesting mush accumulations around the Chiles volcano area. So I'm not surprised about that, but I'm surprised that their receiver function study didn't show any others where we have oodles of other volcanoes. But nonetheless, that's what this study by Koch showed, and I think it was a very nicely done study. And it kind of gave me incentive to use this in this talk here. So this volcano is old. There's a date on it of about 460,000 years at the base of it, and it has a summit of 4,600 meters. It had effusive lavas apparently in its last eruptive activity. There's been one study done on the volcano, and the last eruption was possibly produced lava flows 20,000 years ago. There's another little volcano over here that's related to, it's not a parasite, we don't think, but it erupted about 3,500 years ago with dacites and andesites. But that doesn't seem to have any relationship to this bigger volcano because there's very little seismicity there. The GPS, as I'll show you on some of the vectors, there's just nothing happening there as far as we can tell. So this is another plain view map of the zone, this volcano with its caldera open to the north. And the area that's the hotspot of activity is to the south of the volcano. And then another area that we never even paid attention to. I mean, Ecuador is not a very big country. It's about the size of Colorado here in the States. And this is an area here that looked like it was possibly just glaciated, which is true. It's all the average elevations here between 3,600 and 4,200 meters. And this area never really appeared to have anything. But here was a larger caldera that's probably extinct called Chalcotin. And that, okay, we knew about it because it put out some big ash flows years ago, well, 200 and some thousand years ago. Here's a view of one of the new GPS stations we put in, and this is the wall of the caldera to the south, where all these alluvial glacial deposits sit. But probably within that whole package, which we can't see yet, is a package of volcanic deposits, because just off of here, there's some strata that's really interesting that I barely looked at, but nonetheless, it says that things happen here. And so now I'll show you Susie Evermer worked here back in 2014, and then starting on the 1st of October, and there was an abrupt onset earthquake swarm of over 5,000 events a day. And the GPS displacements about 1 centimeter horizontal and 1.5 centimeters vertical preceded a 5.6. The earthquake 5.6 was in this area here. And afterwards, the system went quiet for 2.5 years. So these are some of the located seismic events at that time, okay? And we only had 2 GPS stations on the volcano. One was there, and the other was off of the picture here. So we weren't very well equipped at that time. We had 2 seismic stations as well. And what you see, this is some of the RadarSat and Cosmos Skymed, basically the modeling of that of those events. And here you can see with this particular station here at Chiles, right here, that there was a gradual northward, eastward, and up movement right before the earthquake, and then everything basically quieted down after that. And this is the bars of the earthquake. So it's 5,000 events a day are here. Here are the swarms. This is occurring in 2014. Then, as I say, we went quiet for 2.5 years. God bless to have that quiet time. And then you have activity picking up again in 2018. And then 2021 a little bit. And then 2022, bang. It starts on the 27th of May, and then it went on for a couple of months, that is with almost 4,000 events a day. And in that period, we had 110,000 earthquakes that were recorded, all of them about more than a half, about 0.5 magnitude. We have 8 large earthquake families. We have locations in the 2 nests, and this is a swarm of 2023. That is, it hasn't yet pretty much finished. When I say finished, you get accustomed to having 400 to 500 quakes a day, and some of them which are magnitude 2, some even magnitude 4. So these are important things. And we have a flip-flopping here of where these events are happening. So first of all, they occur up near the Chiles, right at the base of that big volcano. And then on the second time around in this period of 2017 to 2020, they're occurring at the base of the volcano, but then they're opening up a new area down at the caldera where I showed you where we put in the GPS. And then we have them going over here again between this is Chiles here again, and then here is between the 2. And the most recent swarm has been at the base of the volcano. So that's why I use the word flip-flopping, because how do you know where it's going to go? We don't know yet why it goes from one to the other. So one of my colleagues who works exclusively almost on this, on do the seismicity here, he located these 40,000 events, and that's from 2013 until now. And basically the lilac color deals with that which is at the base of Chiles volcano, and then this area is the other nest over there. So we have these 2 competing areas, and right now, this area is the one that's in operation, the lilac colored one. So getting to a little bit more, here you see the 2 different nests. And what's notable, as I said, is the abrupt onset from basically not having any activity to just going way up, way up. It's like you have a little hose that's garden hose, and then all of a sudden you have a fire hose of water. So these are earthquakes that are just happening constantly. And
And this period, this last period, then in, in 2022, produced another 5.6 earthquake right over there. Okay. So that earthquake looked like this on the, in GCENT and also on the Comet webpage, a very nice concentric rings. You can see it was a strike slip left lateral on an east-west blind fault right there that had never been identified. This fault had never been identified. It had about 10 or 12 centimeters of offset. In the area where the quake occurred, there were lots of landslides, but nobody could actually find the real, like the fissure in the ground that you can sometimes find. So, and then this is a 2023 earthquake swarm, which is dipping to the east here. And you can see that this little fringe up here and this little thing is a shallow. Those are LP events. The majority are all VT fracture quakes. And some of them, as we see, are up to 3.4, 4.3. And then these others here are LP. So this period draws our attention to this number of shallower quakes that occurred. I wanted to show you then some of the GPS velocity registry that we have, and that is that covering, this is only the last 60 days between March and May of this year, and this is representative of the recent trends of this year. So what's interesting is that this particular station is going northeastward, this station here is going southwestward, and this station is going southeastward. So this is a very definite pattern. We only have 5 stations in the zone. This doesn't show anything. You can see the red is the vertical, and that's only in the last that's in 2 months between March and May. So it's quite definite, the patterns. And in this case, the station that we just saw that had the strongest pattern is this particular one. And this is the vertical right here. So you can see that recently there's been times when it was quite abrupt. The ascent, the rate of ascent was very abrupt between May, and that was coinciding with the swarm here and with the swarm here. So every time there's a swarm, there's a really strong, in this case, uplift. So. And then on the north and the south, we see that this is moving up to the north, like I said, and this is going to the east. So this is that's that, and that's that, and that's that. So why is that? It's probably because in the INSAR we also see, this is on the vertical component. We also see these 2 areas which are mimicking very well what we see with the GPS. Although the GPS doesn't cover the entire area perfectly, but we have a station there, we have a station there, we have a station there, and we have a station there. We do not have a station over here, which would be ideal. But anyway, we're able to see that there's these 2 very, very apparent zones of uplift. And we also see that in the preliminary modeling, and I say very preliminary modeling, with 2 different programs, this is a SARScape, I believe, and it shows that there's possibly a dike uniting the 2 areas, and that would be about almost 18 kilometers long and about 8 kilometers below the Chile summit. Chile summit is 4,600 meters, so it's about 4 kilometers below the ground surface, the actual ground surface. And this is the quake that happened there last year in 2022. And then another solution was done, and it showed that approximately, again, the same dike, but this was using only in 2022, this particular station that we had over here. Since then, we put in another station there, and it's only a year old, so it's not mature yet. And so, as I said, as we get more maturity on our data series, then we're able to do a better modeling of these. But the INSAR also has a certain bad coherence in this area because of the earthquake. So the The volume changes are very uncertain. It goes from 3 million cubic meters to 30 million cubic meters, which isn't a very good constraint whatsoever. So as I wanted to point out, the blue is related to this a line here moving to the north, and the orange is related to that area here, so that's moving to the south. So we have a breaking apart. Literally, it's kind of everything's moving apart as if it's being torn apart. And again, we should put a station down here. So putting it all together in a graphic summary, we have these two swarms that have operated now on 3 occasions, but particularly right now, it's dying down, but it's been recent, since May, and or March rather, and we see that this is literally being pulled apart up at the northern part, and this southern part is also going at least to the right. We can't say so much to the left. It's had 2 different earthquakes, 5.6. And we can see, in terms of looking at the long term, this is what we have in terms of the GPS, going from 2014 all the way up to a couple weeks, or just last week, that we now have almost an accentuation since 2022, which is the same time we've had this very, very strong earthquake activity. So summing up, what does it look like that we have? We have a metamorphic basement around 10, 15 kilometers depth. We have probably, as I showed you, the faults, which are bringing up probably hot fluids. But on the other hand, there might be seals in there. There's been some deep drilling, but they've only gone down 4 kilometers. That is for geothermal purposes. There are hot springs there. They're frequently monitored, and there is no significant changes. I remember what Michelle said. There's no significant changes in the mixture of the gases, okay? There's multi-gas. There's all these other ratios being done, not by myself, but my colleagues. There's no changes. There might have been a change of 2 degrees centigrade in the last time. They have to reconfirm that. But there's 3 or 4 hot springs there. There's another hot spring there, but there's nothing really big happening at the moment. And these LPs happened up here 2 to 3 kilometers below the actual ground surface. The deeper VTs are happening about 4 or 5 kilometers below the actual surface, so maybe 8 or 9 kilometers below the summit of this volcano, and also below this area. So we think that seals have, or that is some kind of a cap that is formed. It does not allow a great change to happen in the surface yet, and that's what's creating, the pressures are coming up, but they're not able to get through, and these VTs, which are actual VTs, are happening. So the conclusions is that this incipient deformation is a precursor and is synchronous to seismic swarm reactivation. And deformation continues at Chile's GPS right now, even after the swarm activity ceases. Seismic nest activity occupies areas next to old dormant volcanoes, and that VT events are concentrated 4 to 8 kilometers below the Chile summit. They're not on the surface, they're down deep. It's not like a hydrothermal system that's within drilling of the top of the surface of the land. And it's probably down in the metamorphic basement where magma there may be body or storages in there. And magma bodies are pushing upward. That's a hypothesis right now, creating this notable deformation. And it's detected, as we saw by the INSAR and the GPS. And therefore, if in the future the magma ascends closer to the surface, and that is, if it could break seals in disrupting the hydrothermal system, like we see that it's happened, for instance, at Yellowstone or maybe Campo Felibre, then deformation may accentuate, and spawning of hot springs and geysers could happen in new areas. That hasn't happened here. We're waiting. And therefore, none of these changes have occurred. And the 2 5.6 magnitude earthquakes in 214 and 222, both on the perimeter of these seismic nests and deformation halos, are likely, or maybe, the result of the disruption of biomagnetic pressures of the stress fields, magnetic pressures that are driving these VT events, driving. I mean, the stress fields of local faults, leading to rupture of these faults. One which we didn't even know about, the other which you can see on Landsat, okay? And basically, as I showed, the preliminary modeling by GPS and INSAR suggests that a dike may be in place, or it's trying to be in place in the direction of northwest-southeast. And it's a hypothesis coherent with the vectors of the main GPS stations, as we saw the breaking apart of at least the two northern stations where we have the stations, and leading to rupture of these faults. And the pyroclastic deposits of past eruptions were water rich, had a high silicon content of approximately 70% SiO2. They were explosive and occurred 15 to 20,000 years ago. So that's the end of my story for now. And we'll be working on it, but I just wanted to share this little tidbit with you to get any feedback, criticisms, or observations. Thank you very much.
Well, yeah. Well, we're a few minutes beyond, so we're gonna have to save questions maybe at the end. And so we need to move on to the next talk, which is by Odysseus Papas, and it's on simulating satellite radar measurements of volcanic eruptions in preparation for ESA's Harmony mission.
Right, hello everyone. So as advertised, I'll be talking to you today about the Harmony mission and some of the work that we've been doing in simulating satellite radar measurements of volcanic eruptions. So I trust that a lot of you will be familiar with the Harmony mission, especially after a couple of very interesting talks about it that we had yesterday. But allow me to reintroduce it to you. Harmony is an upcoming mission, an upcoming satellite mission of the European Space Agency. It has been selected to be the 10th entry in the Earth Explorer program. And its mission really would be the observation and quantification of small-scale deformation. And there is a great number of scientific fields in which Harmony will seek to provide data and answer questions, and you can get an idea of some of them on this graph here. There's stuff related to the cryosphere, the oceans, the solid Earth. But of course, the one that interests us today in the context of this session is Harmony's ability to measure topographic change related to volcanic eruptions. Now, Harmony will be doing all this useful stuff by the magic of interferometric synthetic aperture radar. The mission will consist of two spacecraft, both of which will be equipped with a passive receive-only SAR instrument. And the two satellites will be orbiting in formation with Sentinel-1, in tandem, if you will. So what that will give us effectively is bistatic single-pass INSAR capabilities. And I'm sure you're all familiar with the benefits of bistatic INSAR in terms of coherence, in terms of the measurement accuracy and the overall performance that we get out of it. Now, over the lifetime of the mission, Harmony will be operating in a couple of different orbiting configurations, which have been designed to optimize specific types of measurements that Harmony will be acquiring. The ones we're interested in, namely this production of a dense time series of surface elevation models for evaluating topographic change after volcanic activity, those will be generated in this second mode that you see in the graph here, the across-track interferometry mode. In that mode, we will have the two satellites flying in a passively safe helix formation behind Sentinel-1 with a baseline, a distance between the two satellites that will actually vary a little bit as they go through their orbit. And this is something that I will come back to later on. But what you want to take note of right now is the fact that different parts of the Earth, different volcanoes that are located in different latitudes will be imaged with a different baseline and therefore slightly different performance. Exactly how the baseline will vary, of course, is still something that is being designed, but it will vary probably from about 500 to about 800 meters, like you can see in the graph there. Now, in terms of the topographic change that Harmony will seek to image and quantify, it can be a quite varied scenario in itself because, topographic change and volcanic eruptions are quite varied themselves. We have instances of lava flow and deposits of lava. We have instances of pyroclastic flows. We have growth of lava domes, and in occasions we have collapse of lava domes, or possibly even entire flanks and edifices of the volcano and the surrounding topography. So what we tried to do here in this body of work was to perform a sort of case study where we took high resolution bistatic INSAR data. Specifically, we took TandemX co-SSC data, and we tried to look at a recent volcanic eruption and produce an interferogram, a set of interferograms and topographic change maps for that eruption. The goal here was to demonstrate some of the particular challenges of dealing with INSAR and volcanoes, and I'm sure you're all familiar with the effects of the very steep topography that we often see in these kind of scenarios in combination with the viewing direction and the general viewing geometry of the radar. Effectively, things like shadow and layover can become a really detrimental factor in the DEMs, or topographic change maps, that you produce. And we wanted to demonstrate the challenges and demonstrate the need for a sort of qualitative assessment and possibly masking of any DEM or topographic change maps that are produced. And also, of course, to show the importance of having both ascending and descending acquisitions over volcanic regions of interest, because, again, as I'm sure most of you know, these things like shadow and layover, they're dependent on your look direction, and as that is reversed, whether you're on ascending or descending orbit, it leads to a situation where you kind of need both in order to have a complete and clear picture of what is happening at a volcano. Now, besides demonstrating these points as part of the science mission, we also wanted to generate these high-resolution topographic change maps as a product to be handed over to our colleagues over at DLR, the German Aerospace Agency. So they have been tasked with developing, or rather they have developed by this point, an end-to-end simulator for Harmony. If any of you were at Paul Pratt's talk yesterday, you heard about Heaps Terra. And in modeling what Harmony's output would be in such cases, they require data to serve as input topographic change, as ground truth. And the stuff that we produce here could serve for that purpose. Now, of course, the kind of elephant in the room is the resolution, because we know that Harmony is not going to have the particularly high resolution that we have, say, with TandemX. So there's this obvious question of what exactly will the data from Harmony look like. As an illustration of the importance of resolution, here we have an example of a DEM and a top map from a relatively recent period of dome growth in St. Helens. And in the original data, which was at this very high resolution of 1 meter, you can see some very interesting features that you can still pick out if you subsample that data to 20 meters, but if you were to bring it down to 50, they're completely gone. So we were wondering what Harmony's resolution and data would look like. So what we decided to try and do, and this is completely separate from the end-to-end simulator that I mentioned just before over DLR, but we decided on our end to see if we could somehow subsample our data, our high-resolution TandemX data, to something that would be more in line with Harmony and Sentinel-1 effectively, because they're inherently tied, and see what that perhaps might look like. So we took as our case study St. Vincent La Soufrière, where we had a recent eruption beginning in very late 2020. There was an effusive eruption during which we saw the formation and growth of a new lava dome. From April 2021, we had an explosive eruption, and by the end of that eruption, we saw the complete destruction of both the new and the old lava domes, as well as the formation of a new crater and the deposition of tephra along the rim of this new crater. Now, in this graph, you see a timeline of the events that happened over the eruption of St. Vincent, and it's actually here to illustrate one of the great advantages, one of the more exciting features about Harmony, that is Harmony's temporal resolution. So on this timeline, you see these dots which correspond to measurements of dome growth, which were performed using a drone flights on the ground. And you can see they're quite sparse, and they become very sparse to non-existence as you go further down the timeline. Now, one of Harmony's most exciting features really for this kind of study is the fact that it will be producing DEMs at a regular 12-day interval. So if it was operational over a timeline of interest like this one, we would have gotten at least a dozen DEMs produced over this period, which is quite great in terms of being able to monitor the different stages of the event. Unfortunately, Harmony is not quite yet doing that. So we used TandemX co-SSC data, and we only had access to 3 products. There were 2 pre-eruptive products and 1 post-eruptive product. There was nothing available that covered the actual period of dome growth. So again, you can compare and contrast that with the picture that we just saw of the 12-day acquisitions for Harmony. But nevertheless, this is what was available and what we worked with. So we also needed to have some sort of underlying DEM for our study. And the obvious candidates would be something like SRTM at 30 meters, globally available, could be used for any case study of interest. But in this particular situation, we also had a much higher resolution DEM available. It's a DEM recently made using Pleiades optical imagery with some gap filling with Copernicus data. So that one is a 2 meters resolution, and most of the figures that I'm going to be showing you today are using this high resolution DEM, though we did repeat our experiments also with SRTM and a few other things. So we took our TandemX single look complex pair of images. We did our interferometric processing in gamma. It's fairly standard stuff. We got our interferograms, removed topographic phase, unwrapped them, generated our height maps, geocoded them. Again, fairly standard stuff. And this is the kind of results that we got. So we have the pre-eruptive data up at the top. We have the SLC of the region of interest of the volcano. And for every pixel in our area of interest, we evaluated ground resolution and height precision of the produced DEMs. This was done as a means of quantifying the quality and the accuracy of the DEMs at every pixel. It's actually based on work that Fabian has done before. And we can not only quantify the quality of the DEM, but we can also use it to mask out areas of low quality by setting in an ad hoc fashion thresholds that we do not want to exceed in terms of resolution precision. And you can see an example of that in the topographic change map for the pre-eruptive case, where we would normally expect to see pretty much nothing at all. It should be in good agreement with the pre-eruptive DEM. But you can see obviously this large deformation there that is very clearly because of shadowing effects in the original image. It's a completely anomalous measurement. But if we decide to mask out these pixels of low quality in the DEM, as you see in the grayed out pixels over to the right, we can effectively eliminate those or exclude them from any calculations of further analysis. In the bottom, of course, we have the post-eruptive case, which is the more interesting one because we actually have a view of the topographic change that took place, and we can see it actually a little bit better here. So what we were able to see with the high-resolution TandemX data is a picture that appears to be in pretty good agreement with what has been reported as happening in St. Vincent. We saw the complete destruction of the new lava dome. There's nothing there. There's a new crater formed, this large area of subsidence in the center, subsidence being in red here. And we see the deposition of tephra with two noticeable lumps on the north and south of the rim of the crater. Now, this topographic change map, as I said, was also passed on to our colleagues at DLR to serve as input for their simulator. But we wanted to see if we can simulate Harmony's resolution on our end as well. So we decided to try and subsample our data. Now, we didn't want to subsample the produced topographic change map. We wanted to subsample the original SLC products to try and get single look complex images comparable to what Harmony would be getting, which again is comparable to what Sentinel is putting out. And we wanted to reprocess those through gamma. Now, the subsampling, we didn't want to simply multi-look the image because that would give you aliasing artifacts. So the subsampling was done in the frequency domain. To avoid aliasing artifacts and to create a low resolution subsampled SLC, which I'm referring to as HRM20 in these figures, just for shorthand. It is at 20 meters resolution. And these are the experiments again now repeated with these lower resolution SLCs. Once again, we have our ground resolution and our high precision maps, which we can use to mask parts of our topographic change maps that are not of particularly good quality. And if we look at the post-eruptive case in this situation, we see a picture that does include some subsidence where the crater should be, though it is somewhat misaligned, as we've noticed. And the uplift due to the deposit of tephra is still there, but it's of a lower magnitude than we expect it to be. We noticed a similar situation regardless of what the underlying DEM for measuring the topographic phase and for geocoding and everything was. And we know it's not a fault of the DEM. If anything, moving to something like SRTM, which we then found out had some errors in this area, actually caused more problems than we had before. And we are fairly confident that this is down to an unwrapping error, because this is a particularly challenging case of topographic deformation and terrain. And unwrapping the full high-resolution data was already fairly challenging on its own right. So we're thinking that in the low-resolution case, it basically became impossible to delineate the fringes accurately, and that's why we had these results. So one of the main things that we're focusing on now is trying out different unwrapping strategies to try and see what might perhaps be the optimal way to tackle this particular kind of challenging situations. The good news, on the other hand, is that our colleagues over at DLR, who used these topographic change maps as ground truth as input for the simulator, were able to get results out of their simulator that are much more in line with the original ground truth data, albeit obviously a little bit noisier, a little bit lower resolution, but generally, a much better picture. So that kind of puts more the onus on us to try and work out something better in terms of unwrapping our own data. So the work that I showed you here was primarily work that we did last year, and recently we acquired some extra funding to continue working on this. And as I mentioned, we want to be looking at a few things to improve the performance of our Harmony 20-meter simulation method, particularly when it comes to unwrapping. But also we want to extend our work to a couple more case studies. The first candidates that we're going to try and tackle are Reventador and Fuego. These are not only volcanoes that are in different parts of the world and therefore in different latitudes, imaged under different baseline conditions and so on, but also they exhibit different types of topographic change. We've got lava flows and pyroclastic flows, respectively. And there are also volcanoes that other people in the group have studied in the past, so we have some experience with that and with these particular cases and data already available in-house. So I will leave you with that. I'd like to thank you for your time. Obviously, if you have any questions, I'm more than happy to answer them now or discuss them later. There are, of course, some references to some of the stuff that I was talking about earlier and some of the graphs. And once again, thank you very much.
Thank you. Do we have any questions? Can you get the microphone up? Maybe?
Sorry, thank you. Thank you for the talk. I was wondering, so you talk about like the improvement will be probably to work on the unwrapping. Do you have already some ideas or what you're going to test for the unwrapping stuff?
Yeah, the current unwrapping strategy, because as I said, we were working with Gamma, so we were using the minimum cost flow algorithm within Gamma. We want to try out a few other things. Well, some of the obvious candidates obviously being Snafu. It's actually what I'm working on now, trying to interface the data with that to see if it's any better. Then there is the new Lixo tool that Milan can probably tell you a lot more about, that I would like to try out at some point in the near future. And, I don't know if we're going to have time within the context of this project to look at maybe more exotic options like novel unwrapping algorithms or anything like that, but possibly in the future. But the immediate candidates, as I said, we're going to try and look at Snafu and Lixa. But of course, if anyone has any suggestions of things that, are perhaps particularly well suited to dealing with these kind of challenges, I'm all ears.
And just a small question about the, so here, because of TandemX, you'd only have one before and after, which is a very sparse data set to test. I was wondering, of course, if with Harmony, we expect to have 12 days. that one of the solution will be like stack of, if you can stack pre and post DM, and if it's something that can be tested via the end-to-end simulator, like.
I'm not 100% sure off the top of my head if the end-to-end simulator at this stage can do stacks.
Okay.
But then again, you know, PowerPrats is probably a lot more well suited to answer that. I do though think that the simulator will be available for use very soon. So that is hopefully something that could perhaps we could try out by simulating data in there. Yeah.
Okay, thank you.
Okay, thank you very much. We'll move on now and have probably time for questions, maybe towards the round table at the end. Any speakers? The next speaker now is my co-chair, Paul Lundgren, who's going to be talking about volcano science applications, observation needs from future topographic missions.
Yeah, so this is, so yeah, it was good having that Harmony talk. So this is something that's even further in the future. It has no mission yet, but I'm going to talk about STV, which stands for Surface Topography Vegetation. And we're doing a volcano-related sensitivity analysis study for this. And I have a number of co-authors and collaborators. Alberto Roman is leading the modeling of the flows right now. And then in the future, we're going to be incorporating data sets, including St. Vincent with data from Rafael Grandin and his group, and possibly other data to guide some of the simulation studies we do. So, so you might be wondering, what is STV? So NASA every decade has what's called the Decadal Survey that's conducted by the National Academy of Science, Engineering, and Medicine in the U.S., and it places guidelines on NASA Earth science for the next decade and what missions should be developed, what, et cetera. And in 2017, something called STV was designated as an incubation observable, so something that wasn't, the technology was not viewed as being mature enough in the current decade, but was to be, NASA was to invest in science and technology studies to advance that, such that in the next decade, post 2027, it might be ready to be kind of put on board to become a mission. And so as part of that, they had a one-year study team that developed a 200-odd page document about what, you know, to guide the next decade of investments for NASA. And so we, you know, as part of that, there was, and this is over, of course, the full range of solid earth, vegetation, hydrology, et cetera, anything that might need topography or vegetation structure and topography as well. And so they have, you know, they developed this entire range from science to technology development and identifying various types of gaps. And so what we're focused on here is what we call the knowledge gap, which is really the question, and we're focused, of course, on volcanoes, is really what are the science needs for volcanoes, as opposed to, you know, typically what we do, I think, is we see the highest resolution data, as in the case, say, for St. Vincent, and we say, wow, that's really great. But what we wanted to, from a mission perspective, one of the things in theory, we'd like to do is use what are called OSSEs, observing simulation system experiments, to basically have the science drive what the observation needs are, rather than saying, well, we've got a particular technology, it gives us this, tell us what you can do scientifically with this. And this includes both the observations themselves and also the architecture for the mission. And so what we're doing in this study is we're really trying to understand these volcano topography needs through a series of different types of simulations. One is for dynamic volcano models, so models that connect subsurface magma dynamics and diffusion. what are the needs from the fusion part that along with geodesy would help control parameter estimation in such models. So what do we need for that? Then there's, of course, as you can imagine, there's for hazard forecasting, for flow modeling, for different types of deposits and avalanches, etc. What are the resolutions you might need for those types of applications? And then finally, how do these things, what are the implications for mission architectures, which includes temporal sampling? And so just in some graphics, what this means is we're really trying to use some exemplary data sets, such as St. Vincent, such as in Hawaii and other places, also in the Western Pacific, and how can we connect these to these different types of either physics-based models, flow models, and observations, and more on the hazard side of things. And so right now, today, I'm just going to talk really about the flow part and connecting it with a simple flow model that Alberto Roman has developed, and he has a poster on that. And so just again, we're looking at, again, the surface, looking for flows. We're looking at the Kilauea flow forecasting, and that's what we're doing right now. Eventually, we'll be doing other analyses for different systems, and then eventually the dynamic model implications. So in terms of, so one of the areas that we're looking at is something we looked at before with Kilauea volcano, where during the 2018 eruption, we had flown the year prior with GLISTEN, which is an airborne bistatic Ka-band radar that flies on a G3 jet, and we could do, it does 10-kilometer wide swaths of arbitrary length, and we could cover in fact, the entire flow field with one swath, but we actually had many swaths in different directions. And we also, of course, there was the caldera collapse as well. But we're going to focus here on this. And so we had a GLISTEN acquisition before, but we also had we were very lucky in 2018 to have a bare earth DEM, LiDAR-based DEM that covered this area. You can kind of see the edge of it right here. And then for the other areas, we had a TandemX 12-meter DEM. So if you difference the pre-eruption GLISTEN with the LiDAR, because GLISTEN being Ka band is sensitive to the top of the vegetation, you essentially have a vegetation height mass. And then as you go into the eruption and you difference that with the pre-eruption GLISTEN, you get something like this. But of course, where the lava goes through forest, you get negative topography, so negative thickness effectively. And so, but in the end, when you add these together, you get the final flow field. Now, of course, the key thing here was we actually relied on HBO to provide outlines of the DEMs because the data is noisy enough that you can't independently really select the outlines of that. So we had to cheat a little bit, which I think down the road will be part of the implication, I think, for any topography mission is to what extent do you need independent data to define things like flows versus being able to rely completely within the data that you've collected. And so again, this just shows the data that we had over time. And you get, if you look at the last 2 days, of course, you get nice things and the channel is filled, and after the eruption, it drains out. So there's some other interesting details that we're not going to probably be able to explore in our own simulations, but I think the key thing is that there are things that we can model, and then there are things that we can't yet model, and we have to try to understand also to what extent we need to be able to measure those as well. So some things like that might imply a higher resolution than maybe the simulations themselves require. So here I'm just going to talk about the flow model that Alberto has
written this summer. It's a simple flow model with a single viscosity, it's isothermal, and yet we think that the first order captures kind of the main works of first order. And we're not, we use Kilauea kind of as a kind of proof of concept that, passes the smell test, so to speak. So it's reasonable in that extent. And again, as I mentioned, it's a similar, simple, nonlinear PDE that's solved, and it has both the topography gradient and the flow thickness coming into it. And so it captures both convection and diffusion. And so we can run these for different topography resolutions. So if we take the original, and this is just 4 hours. It's 4 hours of model time. It took only a day to run this on my laptop, so it's not that fast, unfortunately. But if we take the original LiDAR bare Earth DEM and resample it at 5 meters, you get a solution like this. If you resample it at 25 meters, it turns out they're different, but they're not that different. So, the first thing that we seem to be seeing with these kind of flow models is that, the question is how sensitive are they to the actual resolution, and we don't know the answer yet, but it does seem that it's varying dramatically with the resolution at these scales anyway. And of course, this is with a particular, there's also questions of, this is with 120 cubic meters per second and a viscosity of 10 to the fourth. So, these things can vary with the physics as well in the solution. And so as I mentioned, that's kind of the proof of pass the smell test if you can fit Kilauea, or when we move to domes, if we model St. Vincent or other places, that kind of serves as a guide to what we put into the model. But what Alberto's doing right now is a more systematic approach of looking at taking, say, something very idealized, like just a planar ramp, and with some, there we go. So the question is, if you take a planar ramp, you add some noise to it, what are the effects on solution? So in this case, you've got a ramp that's dipping in this direction. If you have no noise, of course, you get what you would expect, and these have been benchmarked to analytical solutions for simple cases. But when you add, in this case, half a meter of standard deviation in the noise, you get, it looks pretty similar. There's a little broadening, but it's also retarded in time. So there's a delay there. So that's another aspect to consider, is because when it comes to actual for the USGS, or somebody that's trying to predict flow advancement, understanding that there would be trade-offs in topographic noise versus whatever parameters you have to put into the model to try to fit where things are at a certain point in time in order to maybe predict where it will go and how fast in the future. And then of course, as you go to higher amounts of noise, things start to break down a bit and get somewhat interesting, but again, it can have a deteriorating effect on the solution. And so finally, the other thing that Alberto's played with is putting in some obstacle, and when you do that, of course, it goes around the obstacle. But again, as you have as you add noise to that, it both degrades the solution and causes some delay. So in terms of both the spatial aspects of the DEM and then the eventual temporal sampling you might need in any future observing system, those are the kind of things we're trying to explore. And so with that, so the key takeaways is are that, this is something we've really just started, so we don't have any real, meaty results yet, but we're trying to, we'll be presenting a little more at AGU. And so again, as I just showed, we're looking at these simulations to try to understand the effects of noise levels, coming up with metrics whereby we can assess both on coverage and thickness. There have been a lot of studies where people have been looking at trying to understand the fidelity of different flow models to existing flows, observed flows, and how well they perform. And usually that's done in terms of the spatial coverage, how well it matches that. But we have to consider thickness as well as important. And then, as I mentioned, time will be another aspect to this. And another thing I didn't get into is then when you have these, in the case of Kilauea in 2018, of course, new flows will impact where the next fissure outbreak is and where its flows go. And so that's another consideration, not so much in terms of the fidelity of matching, of modeling the next flow in terms of if you used an old DEM that wasn't updated, but it certainly implies that for the mission, if you want those simulations to be accurate, you would need to be updating your DEMs accordingly. And then, as I mentioned earlier, just other things that we're kind of not considering yet, but might become important are things like flow boundary detection. Can we do that independently of bringing in some kind of optical or other kind of imagery that would be independently used to define that? And then, of course, eventually, one would like to have increased physical realism in the models, but for now, we think there's a lot to be gained just in terms of relative simulations based on this relatively simple physical model. And so the final thing is, I would encourage you to go see Alberto's poster, which for more details and for a more thorough explanation of the method. And with that, thank you.
Okay, thank you. Are there any questions for Paul? Well, I can ask a question.
Okay.
So the simulations you showed look to be very much like shield volcanoes like Hawaii. Do you think it would make a difference if you tried this as stratovolcano, a very steep-sided, narrow drainage channel? The resolution of your topography might make more of a difference?
Well, that's one of the things we're going to be exploring. So we started with this, and of course these are I think that, so the more viscous the flow, in some ways, the less likely less sensitive it might be to kind of very high frequency topography, whereas very thin, low viscosity flows might be more easily deflected. But another thing that we're also want to consider is, and I think it's important for physics-based models, is when you get the case of very small domes, when they're just starting, so the surface, the area that it covers might be quite small, then I think resolution might be more important, whereas, of course, if it gets bigger, you can have a slightly coarser resolution in your DEM potentially. And so, and of course, in these physics-based models, in the beginning, the trajectory is very fast potentially, and that could be more critical potentially for future prediction of where the system will go. So,
any other questions? Okay, in that case, we'll close the session and have some coffee, which you all look like you need. And then we will be back at 4:10 for the Volcano 3 session.
it's great being able to harmony.
Yeah, it's very nice.